Assalamu alaikum students. Today we are going to have our first online class of electrical network analysis lab. We are starting with lab number 2 as we have already done with lab number 1 in our class. So this lab is about the first order RC circuit in which we are going to study about the transient behavior or the transient response of first order RC circuits. Before moving on towards the lab, we will first discuss about what are first order RC circuits and what are first order circuits in particular. So the first order circuits are the circuits in which there is only one storing element is present. Now we know that what are the storing elements we have. We have two types of storing elements. One is the inductor and one is the capacitor. So if it is written that it's a first order RC circuit, then that means the storing element present in those circuits is the capacitor. So we are going to discuss the behavior, that how the capacitor behave in these RC circuits and how the overall circuit behavior changes because of this capacitor. So before moving to the lab, we will first review the basics of how capacitor gets charged and discharged through a simple presentation I have made. Let's just go through it. Okay, so this is the circuit in which resistor and capacitor is connected in series with a supply voltage source, DC supply voltage source, through the switch. Okay, so the first of all, okay, so this RC circuit is so this is a series RC circuit in which R and C are connected in series. So first, at first time when the switch is open, we can say that there is no supply reaching out at resistance and capacitance. That means the voltage across this resistor and capacitor as well as the current will be zero at when the switch is open. So we can say that VR is equals to 0 volts and VC is equals to 0 volts when the switch is open. When the switch is closed, at very instance when we have just closed the switch and the time at when the switch is closed and time is equals to 0, this supply will start supplying the current and the voltage, and this voltage will appear across the terminals of the resistor. Since resistor is not the storing element, so it will act or it will operate at the very instant the supply will start supplying. So this supply voltage will appear on the terminals of the resistance, and at that very time the voltage across the capacitor will again be 0, because it will because there is a property of capacitor that it tries to maintain its original value, or it tries to remain in its initial voltage. So the initial voltage of VC was 0, so it will try to maintain that situation, and the voltage across this resistor will be equal to the V supply. So we can say that when the switch is closed at t is equals to 0, VR is equals to Vs, and in this case if we have taken, let's say, Vs is equals to 12 volts, so it will again be 12 volt and Vc will be equal to 0. And again I will say that the capacitor takes some time delay when while changing its condition, either from charging to discharging or discharging to charging. So, but after some time when some time will be passed, the voltage across this resistor will become 0 and the capacitor will start getting charged, and once it gets fully charged, after some time when the capacitor will get fully charged, this supply voltage, whatever this supply voltage, will appear over here. How this appear over here is that when it's a property of a capacitor, when it gets fully charged, it acts as an open circuit. So when it gets fully charged after some time, so these terminals, the capacitor will act as open circuit, so whatever the voltage will be here will reach over here, because there will be no current, so this voltage will be equal to this voltage as the terminals are open. But again we see that there is this value of volt. So now how does happen that once the capacitor was getting charged, what was happening? So there was since the capacitor does not allow the DC current to pass through it, but what happens is that capacitor takes this charges from the supply and starts storing these charges across its plates. Like the positive charges will store across and will store on this plate, and the negative charges will store on this plates. Once and it will keep on storing these charges until it gets fully charged. So once when it will get fully charged, what happens is that it does not allow further current to pass through it, and thus it acts as an open circuit. So what happens that when it's so there is, since there is no current passing through the circuit, and we know that the voltage across this resistor is equals to the product of I into R. Since there is no current, that means the voltage across the resistor will become zero. And again, the voltage since this is acting as an open circuit, so whatever the voltage we are having here, we will get over here. So the important question over here is that it is mentioned over here that after some time Vc will is equals to Vs, and if we say that this situation comes when the capacitor gets fully charged. But the question over here is that when will the time, what is that time, how much time does the capacitor takes to get fully charged? To know that time, we have represented in a graph the voltage across the capacitor with respect to time, and we see that the capacitor takes this amount of time to get fully charged, and when it gets fully charged, this Vc is equals to Vs, that is the supply voltage. So to know how much time this is this, we are representing this graph in the form of equation. So if we represent this graph in the form of equation, we get Vc is equals to Vs multiplied by 1 minus e raised to the power e power minus t upon Rc. This Vs is supply voltage, and this E is the inverse of natural log, and this T is the time, our independent quantity time, and this Rc is the product of R into C. The important point over here in this while seeing this equation, we get that when it's get fully charged, I again repeat that we are concerned about that how much time does the capacitor takes to get fully charged. And now from this equation it is visible that when it gets fully charged, Vc is equals to Vs. Okay, so that means what? That means we must know the value that at point when this thing becomes equal to 1, or Vc is equals to 100% of Vs. So to make this, we must know the value of Rc. That means that this Rc is really important. Since this T is the independent quantity time, we cannot control it, but this Rc is the controllable thing. So it varies in different circuits. The value of in different circuits, the value of Rc are changed. So the time taken by the capacitor will be changed. So it all depends upon this time constant, that is Rc, and we represent this Rc with a Greek letter that is called as tau. So this is the time constant. Now to know that how much time does any particular capacitor takes to get fully charged, we will apply different values of t, and then we will see the result at what happens. So to do that, we are going to have different values of t, and then we will insert these values in the equation, and then we will see that how much time does it take. Okay, at first we have taken the value of t is equals to 1 tau, that is 1 Rc, and we have inserted this value in this equation, and we will get it Rc cancelled with each other, and we'll get 1 minus e power minus 1, and when we'll calculate its value, it will be having we will be having the value of 0.632, and when we will convert this value into the percentage, Vs multiplied by 0.632, and when we'll continue when we'll convert this value into the percentage form, we will get Vc is equals to 63.2% Vs. from this information, we are assuming we are getting that at when time is equals to 1 tau, that is 1 RC for any particular circuit, RC circuit, the capacitor gets 63.2% of supply voltage. This charging voltage is equals to 63.2% of the supply voltage. That means at the time is equals to 1 tau, it does not get fully charged, it just get the 63% charged. After this we have applied t is equals to 2 tau, and we have seen that capacitor gets 86.4% of its fully charged value. And then 3 tau, we'll get to know that 95% of the capacitor is charged. At 4 tau, we get to know that 98.2% of the capacitor have got charged. And finally at last, at t is equals to 5 tau, we got to know that capacitor is now almost fully charged. So from this we can say that at time t is equals to 5 tau, we have capacitor fully charged. So now we know the time when the capacitor is fully charged. And for the discharging again, to discharge again, capacitor takes this much amount of time to get fully discharged as well. To see this, now let's move back towards the lab manual. So this is your lab manual, which is also posted on LMS. So this is the equation of tau that is written over here. That is the time constant RC. And this is the equation for the capacitor charging, and this is the equation for the capacitor discharging. So we saw that capacitor, the pattern of capacitor getting charged is something like this, and again for the discharging, the pattern is something like this. Okay, so so this was about when the DC supply is attached to the RC circuit. When we apply the AC supply to the RC circuit, this charging and discharging repeats. Why? Because in AC circuits, we know that the positive cycle and negative cycle repeats. In the positive cycle, the capacitor will get charged, and in the negative cycle, the capacitor will get discharged. Because we know that in the positive cycle, the battery supply the voltage, and the negative cycle, battery consumes the voltage or just energy. So, coming back towards the lab, that is the first part of the lab is pre-lab. In the pre-lab, let's just read it out once. Calculate the time constant for this circuit. By using equation 1. Equation 1 is tau is equals to RC. For R is equals to dash and C is equals to dash. Since the values of R and C are not mentioned, that means it's our own choice, or we are not restricted to use some particular value. But I would instruct you to use your voltage as the value of your resistance and capacitance. Let's say, for example, if your voltage is EE-1811 EE-1811 let's say 20 EE-1811 so take the first 4 digits. Since your roll number is of 6 digits, you have 6-digit roll number, so take the first 4 digits of your roll number as the value of resistance and the last 2 digits as the value of capacitance. So let's say your first 4 digits of your roll number is 1811, and you will insert the symbol over here, that is ohms, and then the last 2 digits, it's like 20 micro. Again, take that 2 digits with microfarad, so microfarad. Okay, so you have to take, so every student will have to take their roll number as the value of resistance and capacitance. I have shown you that how you are going to take the value of your roll number. The first 4 digits as your resistance and the last 2 as your capacitance with micro. Okay, now to calculate the value of tau, we will simply multiply these two quantities, and to get this, I will go to calculator, and it's like 1811 or you can say it's like 20 multiplied by 10, sorry, 20 multiplied by 10 raised to the power minus 6. So it becomes this multiplied by 1811. Okay, so the answer is 0.03622. 0.03622. The unit will be second. Second, or the unit is also ohms farad. Okay, you can write both anyway. So now there's another part is set up the circuit in Ltspice as shown in figure 2.1. So now this is the main important part. We are now going to implement this circuit and see the behavior we have studied theoretically and observe this. We are going to observe this behavior on this simulator, that is Ltspice. The link to download and install this software is given on LMS. You can go and download and install from there. Once you do it, the icon will appear here, so you will double click it, and so this is the main window for Ltspice. To get the schematic window, you will have to select the new schematic from file option. So now this is your schematic window. We are going to draw our circuit on the schematic window. So the circuit was RC circuit, which is also drawn over here. You can take the reference from here. Okay. So the first thing is we have to select the components, that is R and C and the supply voltage. To get the components, we can go over here, edit, and we have got the multiple options for any component we want. But there's a shortcut for every option over here, is present over here. If we recognize the symbols, then we can easily select the components. So we recognize the symbol of resistor, that is this. So we will take it, just click it once, and then it will appear over here. Okay, so it is still moving. That means we have not placed it on the schematic. It is still moving. While it is moving, I will rotate it, this resistor, to have its horizontal position. So to rotate it, I will I will press the keys, that is Control plus R. So it is now rotated. I will now click it once with my cursor, with the mouse, and then it is now stacked on the schematic. So now once I have done this is extra resistor is present over here. It's still moving and waiting for it to get placed, but since I don't need this, so I will not use it. So I will just remove it while pressing the button escape. Since it is still in the moving position, then I can remove it while by pressing the button escape from the keyboard. Okay, so the next option, so the next component I need is capacitor. So this is the symbol of capacitor. We all know it, and we will take it, and I'm just clicking it once, and then placing it over here. The extra capacitor will be removed by pressing the key escape. I have done it. Okay, so now the other part is what I need is the power supply or the voltage supply. For the voltage supply, since I cannot find any symbol for the voltage supply, now I will go to this thing, that is the component symbol. Now I will get the component library from here. So this is the symbol library or component library. I will now, since I want voltage supply, so I will search for voltage, and now I have got this voltage. So I will press OK, and now I have this moving voltage supply. I will click it wherever I want it on my schematic. Okay, now this extra voltage supply will be removed by pressing key escape. Now another thing I want is the ground. This is present over here. I have taken it. Okay, extra removed. Now what I want to do is I want to connect these components through wire. So this is the symbol for taking wire. I will select it and connect every component with each other. This is very simple. It is similar to it is very much similar to, okay, this is the extra wire, so I will delete this extra wire. To delete anything on this software, what do we need? We need just press the button delete on the keyboard, and this scissor will appear. So so the scissor will appear. Now click with this scissor whatever you want to delete. Now I want to delete this thing, and then again press escape to escape it. Again taking wire, so we'll connect this thing with this, and okay, So now I'm done with it, and I'm again pressing escape to remove it. Now my circuit is complete. Now I have to insert the values of resistor and capacitor, like we have calculated, or we have takes chosen from our roll number. So just right click on any component, and then we can insert the values. So the value is 11811. Press OK, and here the value was 20 microfarad. So for the micro you can write U. For milli you can write small m, for kilo you can write k, and for micro I'm writing, and there are other symbols like pico for p for pico, and so on. So for micro I'm using U. Press enter. Now we have chosen the value for resistor and capacitor, and let's see what our manual says for the value of voltage. So this is the manual. Okay, this manual is uploaded on LMS. You can take it from there. Okay, for this third step, apply 5 volts peak to peak square waveform with lower level at 0. Okay, so what I'm going to do is now right click on here, and so this is since this is a DC supply, now I want to convert this supply into the AC supply. So what I'm going to do is I'm going to, for the advanced option, since I want a square wave for the AC supply. So I'm going to the advanced option, and in advanced option there are multiple functions. So this window is just like the window for a function generator, where we have different functions for, like, we can have square wave, we can have a triangular wave, we can have sinusoidal wave. So whatever we want, we can take it from there. So since we want square wave, it is instructed to us, so we will take pulse. We'll select this pulse. So all of the options for the pulse wave appear over here. Now let's just have a view of what are these options. So the first option is V initial. V initial is the initial voltage, like when we switch on our supply, what I want my initial voltage to be. Since it is instructed, we are instructed to use 0 volts as an initial voltage, like when the switch is on for the power supply, the initial voltage should be 0 volts. Another thing is V on, like after when it will switch its position from 0, and since it's a square wave, it will switch its position from 0 position to some particular value. Now what that particular value we want, we can have that particular value as 5 volts, which is all instructed to us. So the square wave will be from 0 to 5, and then again 0 to 5 will be the periodic square wave of 0505. Okay, now this is important, that what is this T delay, T rise, T fall. So T delay is the time delay taken by the supply to supply its voltage. Like when we turn on or switch on our supply, there is some time delay taken by the supply to supply the voltages. This time delay is very minute, but it's still over there, but it still exists. So we can, in ideal scenario, this time delay should be 0. But obviously we know that in practical, in hardware, there is some time delay in working of every device. So this supply will start working after some time delay. Now we want to have this time delay very minute, so we will select randomly a very minute number by pressing 0.00000, whatever this, we will going to the closest value to 0. So a lot of zeros are inserted with 1. Okay, so that it's not completely 0, because we want to show that we are working on a practical device, and it's very near to 0, that our device is working very fine. Another thing is time rise. Time rise is the time delay taken by the waveform to shift or to switch its position from lower voltage to the higher voltage. We know that the lower voltage is the 0 and the higher voltage is 5. So it will take some time from switching to from 0 to 5. So this time is the time rise. Or again, this time should be very small or minute. So I'm again taking it 0 point, lots of zeros and 1. Okay. Similarly, Since the switching always takes time, takes some minute time, since the rise time takes some time. Similarly, fall time, like coming from 5 volts to 0 volts, like since it's a periodic waveform, so coming from 5 volts to 0 volts, it takes some time. This time is called as t fall, and we will again take this time as very minute time. Okay. Okay, so okay, the next thing is that T on. T on is the time duration when my voltage is on the higher part, like this thing. This is my this is my V on. So the time taken by the voltage, time taken by the waveform when it is on at this stage. Okay, so since now we have two options. We can select this time, since the supply, when we talk about the power supply, it's all on us. We are independent of taking whatever the supply value we want. We can have any value we can take, but it is for an engineer, it's important to take every step in a calculating manner, so we can calculate what could be the optimal time t on for the waveform. So let's just take okay, let's just have a demo for the randomly selected t on, and then we will see that how we should take this t on. Okay, so I'm just at this point I'm just selecting this value of t on randomly, like 0.00686, and okay, now what is this t period? T period is basically the time taken T period is basically the time period. Okay, now everyone knows that what is time period. Period is the time taken by the waveform to complete one cycle. So since it's a square wave, in square wave we know that the on time is equals to the off time, and T period is equals to T on plus T on plus T off. So since it's a T on plus, oh okay, now there is one more thing I want to show. So this is the waveform graphical representation of where is time delay and where is t rise and t on and t fall. So this is when there is an initial condition when the switch is on. This time is the time delay taken by the supply to turn on, and then from this initial position to this position, it will take t rise amount of time, and then this is the on time, and then again it is switching from this position to this position, so it will take t fall amount of time to switch from this position to this position, and the t period is t rise, like this whole waveform, to get to complete one cycle. So t period is equals to t on plus t off. Since it's a square wave, so t on is equals to t off, so t period will become twice of t on. So I will calculate what is the twice of this, 0.0086. I'm not taking it 0.0086. I'm just taking a random easy number which I can calculate easily. So 004, I am taking 004.008. It's twice of this number. So now I have selected how my power supply will work. Okay, so I will press OK over here. So now I have seen that the details of this supply have started appearing over here, but since these are the long details and I find it unnecessary, so what I'm going to do is I'm just going to make this information visible on schematic. I'm going to uncheck this, okay, so that it just does not look bad. I'll press again OK. Okay, so now my circuit is complete, everything is done. Now I'm going to simulate it. Once simulation, before starting the simulation, we know that we are going to set our oscilloscope, the function or the display of the oscilloscope, and here we are going to change the display, or to set the display of the oscilloscope. We are going to click this button simulate and go to edit simulation command. So once we'll select this, a window will appear like this. it is giving me different options, like whatever we want to do. We want to do the transient analysis, that is the time domain analysis. We want to do the AC analysis, DC sweep. There are many other options. We will explore these options in the further labs, but since at this point we are concerned about the time response or the transient response of the RC circuit, that how at different times, at what time does it get fully charged or discharged, at different times how it behaves. So we are going to have the transient analysis. So in this analysis, it is asking me about the stop time, like it will start from it, since it's not asking about this start time, so that means it's obvious that it will start from 0 seconds. And now it is asking me to have the stop time. So to select the stop time, we need to have the information that what our supply voltage or supply frequency is, or supply time period or supply frequency is. Since the time period I have selected was 0.008, that means what? That means that one cycle of the supply, either it is whatever the shape is, one cycle of the supply will be completed in 0.08 seconds. 0.08 seconds. To observe this one complete cycle, or to observe the multiples of this one complete cycles, we will have this stop time at that point. So 0.008 for at one cycle will be completely shown at stop, if we take stop time 0.008, and if we take 0.16, we will have to observe, we will be observing the two cycles. So it's good to have observe two cycles rather than just one. So it's on our choice, and we can observe one as well, or two or three, whatever. Okay, so I'm pressing OK. So this is again, the information is moving for the simulation command. So I have just clicked over here. Okay, so now my circuit is completely ready to be run. So now I'm pressing this icon, that is for run. Okay, so now this oscilloscope window, you can say the simulation window, it has appeared over here to observe different parameters we want to observe. So now we have multiple options, whether we can observe the voltage across capacitor, we can observe the voltage across resistor, or voltage across the supply, or voltage across resistor as well as capacitor, or the current going through this and that. How? So we will see. So this is, we can say I am on this window, I'm clicking on this window, I have clicked on this window, simulation schematic window. So now you will see that since I'm moving my cursor over here, there is nothing happening. Once I will take my cursor over here, you can see that if I'm placing my cursor on any of the component, this symbol will appear. This symbol is shows the this symbol is for the CT symbol, that is a current transformer. Current transformer, as we all know, that used to measure the current. Okay. So this is our current transformer. This will tell me the current, or the wave. It will show me the waveform for the current passing through this resistor. If I place this cursor over this capacitor, it will tell me the direction, the behavior of the current going through this. And if I place it over here, it will show me the current for the supply voltage. And now you can see that if I place my cursor on any of the node of the circuit, the symbol is changed from current transformer to this probe. This is the probe, and we all know that the probe is used to measure the voltage. Okay, so now one more thing that we know, that for the voltage, to measure the voltage across any component, we need to have two probes. Okay, the one is for the positive and second one is for the negative. Now since there is only one probe coming over here, then that means that we can another probe is by default is being over here. That means the voltage, the reference probe, that is the reference probe, is always this ground. Okay, so wherever since I have placed my cursor over here, this probe is over here. That means it will give me the voltage across at this point to this point. And in between these 2 points I have a capacitor, so it will give me the voltage across capacitor. And when I will place my cursor or probe over here, then it will give me the voltage for resistor as well as capacitor. How? Because from this probe to this point I have two components in between, resistor as well as capacitor. So it will give me the combined voltage, or you can also say that it will give me the voltage across this supply, which is obviously equal to each other. So now, since we are only concerned about the voltage across capacitor, so we will insert our probe over here. Okay, so this graph is giving me nothing, rather just a raw information. I'm not getting anything from this graph. Although it's a voltage across capacitor, but this graph is not giving me any useful information. So why it's not giving me any useful information? Because the value of this supply was taken randomly. We did not calculate the actual supply or the frequency we should give to observe the particular waveform, or to observe the exact charging and discharging of the capacitor. So now we are going to give the calculated value of this supply frequency or supply time period. So now we are going to close this window so that I can again come to the schematic window. Okay, so now the value of this supply voltage will be changed according to the values of this resistor and capacitor. From the value of tau, we came to know that from the value of tau, this is like 0.03622, we came to know that capacitor will take 5 multiplied by this time amount of time to get fully charged. To observe the fully charging of the capacitor, like to observe this kind of behavior of a capacitor of getting it fully charged, we need to have the supply voltage of, we need to have the on time of the supply voltage equal to the 5 tau. That is so that we may observe the fully charged value. Okay, so okay, so what I'm going to do is I'm going to multiply this time multiplied by 5, this thing multiplied by 5. So now I got to know that the time taken by this to fully get charged is 0.118. So now I will have the 0.1811. Okay, so now this t on will not be randomly selected, but it will be equal to 5 tau. Why? Because I want to observe the waveform when it will be fully charged. So what was that? Sorry, I forgot. 0.1811. 0.1811. So this t on will be multiple of it, multiplied by 2, 3622. 0.3622. Okay. So the total whole waveform is completing in time period 0.3622. So for the simulation window, for the oscilloscope window, I will restrict this 0.3622, right? So 0.3622 will be the time for one waveform, and if I want to observe two particular cycle or even one, so and okay, let's just take it 0.5, so that 0.5, so that I will have the bigger view. Okay, I will click on OK, and then we'll again run this, again measuring the voltage across capacitor. Okay, so now we have seen that this voltage has got fully charged at this point, and is again okay at this point. Okay, so once it is get fully charged, and then it will start discharging. Then again the cycle repeats. So how do I know that it has got fully charged? Because at this point its voltage is equal to supply voltage. Supply voltage was 5 volts. So this was the thing that now I have got to know that it is getting fully charged at this point, and there is no extra time taken in this on period. Once it is get fully charged at this point, it has started discharging, because we have given this time period in a particular manner that it should get the exact time, that is 5 tau. Now let's come back towards the manual. In it is mentioned that okay, we have already done it. Now observe the, okay, we have done it, that was coming to be 5 tau was 0.1811. So 0.1811. Okay. Uh, so the unit is, you can write unit as seconds, or you can write unit as resistance in ohms farad. Okay. So the next step is, okay. So so this is the next step. Observe the circuit response in the following three cases. Now we are going to observe the response of the circuit while taking the three possible cases. Okay, the first case is when the T on is very much much greater than 5 tau. We know that it gets fully charged at 5 tau. Now we are going to observe that what is the behavior when T on is far more greater than 5 tau. So this they have given us that you can take this far more greater than value, not randomly. You can take randomly, but you can also take it as 15 tau. So from the calculator we will. So this is 5 tau. So this was the actual value of tau. Now we are going to take it as 15 tau multiplied by 15. So the value becomes 0.5433. So now I'm going to close this window. To come back to the schematic window, right click on it, and then the value here is 0.5433. 0.5433, and it's multiplied by 2, 1.0866. Okay. So I have taken this time far more greater than the 5 tau. That means it should show the behavior that after getting fully charged, it will continue showing the Vs is equals to Vs, Vs is equals to Vc. Click on OK. I will again change the edit simulation command till it's for 0.5, and my T period was going beyond 1 second. So I'm going to take this as 1.5 seconds. We'll click on OK. And then run it, and then again we'll observe this behavior. So now we have seen that at this particular time my capacitor has got fully charged, but it continues on at this state. Why? Because there is still it is still getting supply from the power supply. Once the cycle is complete, T on is complete, now it will start discharge. It will start discharge, and after this it will get after it has got fully discharged, it will continue at this state. Why? Because there is still no supply from the power supply. Once again it has stopped, it has gotten the supply from the supply, it's got fully charged, and continue the state while it is getting from this supply. It is similarly that once the device has got fully charged, it will remain on that state because it is still getting the supply from the voltage, and it will have this voltage across this capacitor as similar as this supply. Supply is 5 volts, so similar appears in here. Or we can also observe the voltage across resistor later on in this scenario. We will first do the other cases and we will observe the voltage across here. Okay, so once we have done this, okay, so they have also asked us to measure the voltage across capacitor as well as on the input. So we will now compare the voltage across this supply. So this is in the blue, we have got the voltage across the supply. We can also change the color of this blue if it is not visible. So we can change this color. How I'm changing the color? To change the color of any waveform, click on its label. This is the label of blue waveform. I don't want this blue because it's not that much visible. So I will right click on here where it is written the label, and then I have got this window open, and then I will change the color whatever I want. So I will take the bright color so that it's visible. I'm taking this color, like this color. Okay, so I will click on OK. So now this is the supply. Still the time it is getting on time, it's getting charged, and then remaining on its state, then discharge, charge and discharge. So this was the first case when this on time is far more greater than the time taken for the capacitor to get fully charged. Now we will consider the second case. Okay, now it has also asked us to calculate the T on. We have already calculated it. Let's just do all the calculations over here. So the calculation for the 5 was 0.5433. So I will write over here. I'm also guiding you how to complete the manual so that you will complete it. Don't forget to write the units of everything. Okay, units are very important. Okay, now simulate and observe the value of tau from the graphical display, and then according to the definition, time constant is the time when the voltage across capacitor reaches 63% of this. So now we are going to observe that whether our theory was right or not. That our theory was at time is equals to 1 tau, our capacitor gets 63% charged. So let's just observe this value. So it's asking me the steady state value of voltage observed is. So we from here it is very obvious that the steady state voltage is, this is the steady state, this is the transient state. Okay, this is the transient state where the voltage is changing, and this is the steady state where the voltage is in steady state and it's not changing. So this voltage is 5 volts. So I will write 5. Okay, so I will write 5 volts over here. Now 63% of the steady state voltage. Now I will now it is observed. I have observed it. Now I have to calculate 63% of the steady state. Okay, now I will go here. 63% is like 0.63 multiplied 63 point what was that, 63.6, 0.636, sorry, 0.636 multiplied by 5. So this is 3.18. So the calculated value for the 63% is 3.18 volt. Now we have to observe the tau, that at this particular voltage, what is this value? It should be equal to this value, that is 0.03622. Okay, so now we have to, since this was calculated, now we are going to observe this, that at 63.636%, what is the tau? Okay, so now by looking into this graph, we have to observe when will the 63.6 voltage, 63.6% of 5 volts is 3.18. We have to observe when the voltage is 3.18. What is the time? What is the value of x-axis, that is time, at voltage 3.18? So for that, I'm going to turn on the grid. From right click on this graph and then view grid. Now the grid is turned on. Now what I'm going to do is I'm going to pan a particular amount of area, because I'm only interested in knowing the value of time at 3.18. So I'm going to pan this area between 3.0 and 3.5, because the value will appear over here. Okay, so so for 3.18, what I'm going to do is that I'm going to further pan this area. Okay, so this will lie, so this is 1.3.1, 3.2, so this will lie in between here. Okay, like something like this here. So what I'm going to do is I'm going to take the now I'm going to take the cursors. Like in oscilloscope, we have the cursor to observe the particular instant, a particular value of x-axis or y-axis at particular instant. So for the cursor, we are going to right click over here, and we are going to measure this thing, that is voltage across capacitor. for whatever the voltage, for whatever the waveform we want to observe its value, its particular value at particular instant, we are going to right click on its label. So this is the voltage across capacitor, its label is over here. I'm going to right click on it, and then the attached cursor is none. So I'm going to attach a cursor, first cursor. I only want one cursor, okay? I don't want two or three cursor. I'm not doing anything further, so I only need one cursor, that is first. I'll click on it and then click on OK. So now this cursor has appeared. So this cursor will move on this waveform. So you can see that I'm dragging this cursor on this waveform. Once I will leave this and will move my cursor over here, so the sign has changed. Where it is written first, since the cursor was first, when my one appear, so now I will click on the mouse and will click on the mouse and then will drag my cursor along this waveform. Since I want my I want to observe the time at V is equals to 3.18. So at this is 3.2. We can also see the value of the cursor right over here. We can see the value of here. So this is the cursor is placed at 3.19. I want to place this cursor at 3.18. Okay, so this is the optimal value, and the so this is the value I have selected. It's 3.184. 3.184 is the value I have selected. Okay, so now so the horizontal value we have observed. Since the horizontal axis we want to observe the time, horizontal axis is 36.74 milliseconds. So now we will compare the value 36.7 milliseconds. So now I'm going to compare this value with the initial tau. So we can say that it's almost similar. This is 0.03622 and the value I have got is 36.7. So I can again 3.18. Okay, so 3.184, 36.7 millisecond. So I'm going to write it over here, 36.7 milli, or you can also say that 0.0367, which is almost equal to this value what we had already calculated. Okay, so what next step you are going to do is you will insert this graph again. Since I have already observed this value, so I'm going to turn off the cursor and we'll select this none. Okay, and we'll go to the fit to page value, zoom to fit, and now what's the next step you are going to take? You will print screen this portion and you have to paste it over here. Okay, so that we can see the observation. Now the second step is you have to take time is equals T on is equals to 5 tau, which we have already done, and then repeat the same steps, and then repeat the same steps as T tau is equals to observed value, and then you will paste the graph over here, and then T on is very less than 5 tau. You will observe this value, the 5 tau. You have to do it on your own, and then you will observe the waveform. I'm doing this step because I have already done these two steps. Now I'm going to do this step, that is T on is very much less than 5 tau. So randomly, they have given us that we have to select the lesser value as 0.5 tau. So the value of tau is it's disappeared. Let's just see what was the value. Value of tau was 0.0362, right? So 0.0362. So this was value multiplied by 0.5. Okay, so I'm going to take the value of T on as 0.0181. So I'm going to close this window, select this, and time is 0.0181, and its multiple would be its twice will be 0.02. I don't know the twice of it. 0362. 362. Okay. Oh, click on OK, and now I'm going to observe the window. I will now shrink the timeline to observe it. Clearly, I'm just going to have it 0.5. Okay, or 0.1. 0.0, it was 0.0, so that's I'm 0.1. Okay, so now I'm going to run it. And again measure the voltage across capacitor. So now you can see the behavior is something like this, and voltage across will be like this. So we now got to see that once this time was there, when the T on, since the time is on, this waveform was not fully charged, and again since it was charging up, but the T off was started. T off got started. So this T off started. This made the capacitor not get fully charged, and then it again started discharging. It similarly, like you charge your cell phone and it gets 20% of your charging, and then you start using your cell phone without charging it. It's similarly happening over here. It wasn't fully charged, then the off time appeared, it started getting discharging, and also it wasn't fully got discharged. Again the starting charging time came, discharging time came, charging time came. So the behavior is not fully informative. Why? Because the capacitor wasn't fully charged. It was not given the due time to get fully charged. Okay, so this was it about the whole practical. You are going to do it. Okay, and now you are going to observe it. Now the second part is the lab task part. So this was the pre-lab part, in which we explored a new software that was Ltspice. Now what I want you to do is that the lab task is similar to the pre-lab task, where if we were in our class, I would ask you to do the lab task on the hardware, like implementing the circuit on the breadboard, etc. But since we cannot do it in this quarantine time, so what we can do is that we can explore another simulator, like similar to Ltspice. One of the simulator we have observed is Ltspice. Now we can also observe some similar simulators as well. Now to do that, what you can do is that you can Google the similar simulators, and you have to do the lab task is very similar to the pre-lab task. If you have got fully understood what's happening in pre-lab, then you will be able to easily perform the lab task. But what I want you to do is that perform it on another simulator, and compare your result with the lab task and pre-lab task. Okay, so the steps are same. After this is the post lab. In post lab, these are the questions that you have to answer, and this is very easy questions you have to answer. Okay, so this was all about today's lab. But now what you have to do is that, now coming towards the LMS part. On the LMS, I'm going to add an option over here, that is add a folder, which is the submission of lab number 2. In this submission, what you have to do is that you have to complete this lab manual, like I was completing while doing pre-lab. Similarly, you have to do it the pre-lab as well as the lab task with the values of resistor and capacitor as your roll numbers. And then after completing this lab manual, you have to upload this lab on LMS. I'm going to add an option, will guide you. So you will be having an option to submit your file here. It's better to submit your file in the PDF form, and you will be very much similar to convert Word file into PDF. If not, then you can ask me. For the simulator, any other simulator, what you can do is you can search for the simulator, like circuit simulator or any simulator. There are many online simulator present, you can explore. I want why I'm not doing it. So this is Circuit Lab. You can also explore it. There are multiple other softwares as well. This is one online simulator, Spice, will be very much similar to the Ltspice. So what I want you to do is explore another simulator and do on your own, so that your skills will be polished to use any simulator at any time, or you want. So you will have the confidence that you can use any simulator. So we will inshallah meet in the next class, or we will discuss the things. If you have any query, you can email me on my email address. My email address is f.akram. I'm writing over here. My email ID is f.akram@dsu.edu.pk. So this is my email ID. You can email me at any time, any query you are having it. So you have to complete this manual and submit it till next week, and I'm going to upload the next lab as well. Okay. So Allah Hafiz till then.